We're going to shift our discussion to properties of liquids and solids now that we've introduced gases a little bit. And liquids and solids are actually very similar, but there are some differences here that we're going to compare. So what we want to look at is this chart. And on the left side of this chart, we're going to talk about liquids, and on the right side, we'll go back in and fill it in about solids so we compare them. And remember, when we're talking about liquids and solids, we're looking at how the molecules are arranged in each, and how the molecules are arranged give the properties of a liquid and a solid. So the first thing we're going to look at is intermolecular force strength, or IMF strength. And remember, intermolecular forces are the forces between molecules. So in liquids, the intermolecular forces are stronger than those in gases because a liquid stays together. It has a definite volume. A liquid is definitely a fluid. It has a very high density because a great deal of mass over a little bit of volume. Are liquids compressible? Can you compress a liquid? No, not really. This is the property that leads into the entire field of hydraulics. How our brakes work in our cars, and the whole area of liquid hydraulics can go for this. So if you're interested in engineering, you'll take entire courses on hydraulics and the compressibility of liquids. And liquids do have diffusion. Think about when you're making a pitcher of Kool-Aid at home and you put the packet of the colored sugar in the water and it diffuses throughout the water. Slower than in gases, because the molecules are moving slower in liquids than they are in gases, but diffusion does take place. So in solids, intermolecular force strengths are very strong. That's what makes a solid, is the fact that the molecules are very connected to one another. Solids are not fluids. They do not flow. An extremely high density for solids. And solids are not compressible either. Diffusion does occur in solids, but extremely, extremely slow. Usually something that could take years to diffuse through. So these are some comparisons and some properties of liquids and solids together. Liquids exhibit a couple properties that are specific just to liquids. One of those is surface tension. And surface tension is what allows water to bubble up on surfaces or to form a sphere on surfaces. And you see the example down here when you have a freshly waxed car and the water beads up on it. Because water has a very high surface tension. It's an attractive force between particles that wants to minimize surface area. And so the shape that forms the minimum surface area is a sphere. And this is also why water falls as drops. That's why we have raindrops. Because picture these water molecules on the outside here, all holding hands because they have strong intermolecular forces. And they want to be as close to every other molecule as they can possibly be. Well, in order to achieve that, they need to form a sphere. Or in this case, when they're sitting on the surface, a hemisphere, a half circle. Some liquids have very high surface tension like water. Some liquids like ethyl alcohol have a very low surface tension. Basically, the more polar the molecule, the higher its surface tension is going to be. Remember, we did a lab earlier in the year where we counted how many drops of water we could put on a penny, and the water went up to like 30 some drops. But then we tested another substance and it was much less because water has a much higher surface tension. There, whoops. All right. This is another reason little bugs can crawl across the surface of water, because of the surface tension of water. Capillary action is something that occurs between the surface of a liquid and the surface of a solid. This is the reason why we see a meniscus form when you measure things in a small graduated cylinder or a eudiometer or a pipette in the lab, because the water is attracted to the surface of the solid or the glass. And so as those water molecules on the side are attracted to the glass, they're going to go up the glass and leave a little depression in the liquid, meaning they're a little more attracted to the glass than they are to themselves. And you notice the difference of the picture on the right over here. You have water, which forms a meniscus, and you have mercury, which forms a reverse meniscus. Mercury in a narrow tube actually bubbles up a little bit because mercury atoms are more attracted to themselves than they are to the surface of the glass. Mercury has a higher surface tension than water does. And so mercury forms the reverse meniscus. So capillary action is a property unique to liquids. Now let's shift gears and talk about solids a little bit. There are two general types of solids. There are what we call crystalline solids and there are amorphic solids. Crystalline solids are solids where the atoms or molecules arrange themselves in a geometric pattern. A cube, maybe, or an octahedral, or a diamond shape, some sort of geometric pattern that's repeating itself over and over again. Amorphous basically means without shape or without pattern. Amorphous solids have molecules that are randomly positioned in there. And there are four types of crystalline solids: covalent network, covalent molecular, metallic, and ionic. And you may remember a lab that we did way back in Chapter 6 when we were talking about intermolecular forces. We did that lab where you investigated the properties of these four types of solids. And then we gave you an unknown how to find it. So we'll go back, just kind of review these a little bit. And by the way, if we're talking about melting points here, and this shows decreasing melting points, network covalent molecules like diamonds have a higher melting point than any of these other ones, and as we go down, the melting point generally gets less. This structure here, table salt, would be an ionic solid because it contains ions, and they're arranged in a geometric pattern, a cube. This over here is a metallic solid, and remember metallic bonding, as we've talked earlier in the year, has a sea of electrons. All these metal cations don't like electrons. Remember, because metal atoms are a little bit bigger, so they want to give their electrons up, so their electrons flow between the atoms. This is what gives metals their conductive properties of electricity and heat. And we call this the sea of electrons. A covalent molecular compound like water has individual molecules that are bonded maybe to one or two other molecules. A network covalent molecule has a structure where every atom is networked to every other atom. It's kind of like a computer network, the way all our computers are networked to all the printers in the school. And so it's a continuous pathway. Here, the individual molecules are together and maybe bonded to two other molecules. Here, you can get to every single atom from another atom. Still forming covalent bonds, but in a network. And the one over on the far right represents an amorphous solid. And notice there's no real repeating pattern or shape to it. And you see the examples given to you there. An amorphous solid, an example would be like glass. Both quartz and glass are silicon dioxide, but it just depends on how those atoms are arranged as to what they're going to form. So make sure you read the paragraphs in your textbook as well. Give you a little bit better definition, a little bit more description of the differences between these types of solids.